Hello everyone, my name is Hok Lai. I'm an online graduate student from WellTech. Tonight, my teammate Francisco Hauhan and I will present our findings regarding acid surfactant solution as stabilization agent for expansive clay. The agenda is that we'll give a brief overview, then followed by literature review regarding the soil stabilization mechanism with acid surfactant, and then we'll talk about the lab experiment that we did and our analysis. Finally, we'll summarize our findings and conclusion. As you all know, stable subgrades are key to optimum performance of transportation infrastructure. But commonly, clay and sandy soils with poor performance characteristics are encountered in the field. That's why we utilize various soil stabilization techniques to improve the quality of the subgrade soil. The traditional and proven type of soil chemical stabilization includes the use of lime, cement, fly ash, asphalt, and etc. These stabilization techniques are completed before the construction of the transportation infrastructure. On the other hand, acid surfactants are directly injected into the soil, which allows engineers to repair subgrade which are already commissioned as part of transportation infrastructure with minimum intrusion. One of the main objectives of this study is to assess the performance of acid surfactant as soil stabilizer and identify best handling and testing practices. Surfactant is a compound that can lower the surface tension between two liquids or between a liquid and a solid. Its most common use is as detergent. Contrary to bioavailability of various acids, surfactants used for soil stabilization are usually proprietary with non-disclosed chemical composition, which make it difficult for detailed analysis. Soil stabilization with surfactants involves surfactant chemically reacting with the soils and improving the moisture density relationship. Surfactants can be cationic, anionic, and non-ionic, with cationic being the most common type. Surfactants are generally organic and contain a hydrocarbon chain, which when comes into contact with clay will replace the cation of the clay soil. This ion exchange results in a partial instantaneous hydrophobic or water-hating effect, which reduces the surface tension of water and the thickness of the diffused double layer by allowing water to flow and dry more freely and easily. Another effect of this is that it lowers the optimum moisture content. Although this effect has no direct impact on strength gain, it eases construction by reducing compaction effort and water requirement, or it increases the density and strength at certain moisture content. If cationic surfactant is used, its cation would be attracted to the clay surface by cation exchange, which promotes a flocculated clay structure. The effect of this is increased strength, reduced plasticity, and reduced swell potential. Soil stabilization using acids has the effect of increasing strength and water resistance. Examples of acid stabilizers are phosphoric acid, sulfuric acid, and citric acid. And these stabilizers are most efficient on clay soil. Its effectiveness largely depends on total fluid content of the acid at compaction and free acid concentration. The chemical reaction between phosphoric acid and clay will produce aluminum and iron compounds such as aluminum metaphosphate. As the reaction continued, the excessive or the free acid would react with aluminum to produce an insoluble cementitious gel, which is aluminate phosphoric hydrate, which would bind the soil particle together. The chemical reaction from phosphoric acid to aluminum is shown on top, and then the chemical reaction from aluminum to this cementitious gel aluminate phosphate hydrate is shown in the bottom. And according to one study, after curing for 8 months, the compressive strain was increased by almost 3 times.